Hey guys, today this will be our third session for LTE KPI optimization and we will cover LTE drop rate today. Previously we have already covered ERAB setup success rate and RRC success rate. So today we will cover ERAB drop rate. As we all know, this is one of the most important KPIs for LTE. Everyone wants to improve their drop rate and today we will understand how we can do that. So let's continue. Let's start with it. Overall, the drop rates can be categorized into two major categories. One can be the eNodeB initiated drops. The other will be the MME initiated drops. So let's start with the eNodeB initiated drops and understand why we call them eNodeB initiated and what are the major causes for that and how we can optimize or resolve these issues. So firstly, the first one is RLC retransmission max out. So in this scenario, what happens is that the eNodeB, whenever it is sending data in the downlink, it has some retransmission threshold at its RLC layer. So let's say we have a downlink data allocation and the UE is not able to decode it. So it will be either a NAC, which is a HARC NAC, or it will be a DTX, which means the PDCCH was not decoded. So in any case, if the UE is unable to decode the data, that means the eNodeB needs to retransmit it. Now the retransmission first takes place at HARC layer. So at the HARC layer, which is more like the physical and MAC layer, you can retransmit data multiple times. If all the HARC retransmissions fail, then the RLC layer, which is the RLC layer, that retransmits the data again. So on the eNodeB side, we have a maximum number of RLC retransmission count. Once eNodeB has tried all the RLC retransmissions and it is still unable to get to the UE, so that means the eNodeB has maxed out its RLC retransmission threshold. In that case, once this happens, the eNodeB will then send a UE context release request to the MME, indicating that this is an abnormal release and the UE is no longer accessible to the eNodeB. So in that case, the eNodeB will peg a drop. Because the eNodeB finds out itself that the UE has undergone a radio link failure and eNodeB has found out itself that the UE is no longer successfully connected, or it does not have a viable radio link anymore. So eNodeB sends the UE context release to the MME. Because eNodeB initiated this, so this falls under a category which is eNodeB initiated. So this is the scenario, the first scenario, which is a common scenario when you have bad downlink quality. So if you have bad downlink SINR, for instance, the UEs will have difficulty in decoding your downlink data. And in that case, you will have more chances of having this kind of failure. Now, how to optimize that? One of the easiest way would be that we just increase the RLC retransmission count. So if let's say we have set it to 8 and we make it 16, that means eNodeB will wait longer. It will retransmit at RLC layer much more times. Instead of 8, it will retransmit 16 times. So there is the probability that the UE might not fail and it might even decode it, let's say at 10th retransmission, so it will not have a drop. So with increase of RLC retransmissions, you can actually improve this KPI. However, the drawback would be that if you have more RLC retransmissions, so a UE that was in bad radio conditions will take more overhead because you're causing more retransmissions, and it can also cause that the UE to have if the UE is connected and is unable to decode the data, that means the UE will have more interruption as well, right? So this can be a compromise. So you have to find the optimum value for your maximum RLC retransmissions. Another one could be the RLC pole timers. So the RLC pole timers, if they are too small, then your retransmissions will happen very quickly. That can also cause a quicker timeout for RLC retransmissions, which can actually result in more drops due to this issue. Again, but if you increase the pole timers to a very high value, then that can cause more interruption time for the UE. Other than that, the most the most significant scenario would be that if you can improve your downlink SINR by physical optimization, for instance. So if you do down tilts, or if you optimize your PCI plans, if you optimize your layering strategies, you can improve your downlink SINR. In that case, this issue should be reduced anyways. So that is some of the cases that we can do, some of the optimization actions that we can take to improve such a scenario. Let's move on to the next possible scenario. Now, another possible scenario is a handover initiated drop. So consider this scenario where eNode B1 has started a handover towards the eNode B2 for this UE. So it sends the handover request over X2. eNode B2 says X2 handover acknowledge, and based on that, the eNode B1 will then send an RRC connection reconfiguration, which will carry the handover command to the UE. Now, if the UE tries to finish the handover, it needs to send the RRC connection reconfiguration complete to the target eNode B, which is eNode B2 here, and in that case, once it completely sends that and eNode B2 receives it, then we have a successful handover. But what if the UE is unable to complete this part, and during this time the eNode B1 will have an X2 relocation overall timer. Now this timer is something that the eNode B1 starts after it has sent the RRC connection reconfiguration to the UE, and the timer is it stops when it successfully gets the handover successful intimation from eNode B2. But in this case, because the UE was unable to reach the eNode B2, so the eNode B2 will never send a UE context release to the eNode B1 telling the eNode B1 that the handover was successful. So the eNode B1 will keep waiting for the X2 relocation overall timer, and once this timer expires, the eNode B1 will send a UE context release request to MME, which will be an ERAB drop because the handover was not successful. So eNode B1 will assume that the UE had a radio link failure, and once the timer expires, the eNode B will then send a context release, which will be an abnormal release, and we will call it a drop. So this is a scenario where we have a handover drop, and again, because the eNode B sent the context release, so it is an eNode B initiated handover drop. Now what can we do for that? Again, if first thing would be that if this timer is too small, so yeah, you can increase this timer value. Other options mostly that happen in this scenario is that you have to do neighbor optimization. So because this failure is in execution phase, that means that the eNode B1 had already made sure that the UE had met the, let's say, A3 or A5 or A2 thresholds. So it means the UE already had met the target RSRP threshold. That means the UE was within the eNode B2's coverage. So it is in the execution phase. So it can be because of the issues on the eNode B2. It can be because of cell range issues. Let's say eNode B2 has a very low cell radius, for instance. It can happen if eNode B2 has lots of signal fluctuation. In that case, what we can do is that we can increase the threshold. Let's say if A3 was 2 dB, we can make it 4 dB. We can increase time to trigger. If it was, let's say, 120 milliseconds, we can make it to 40 milliseconds or higher, whatever the values we have. If it is only specifically, we find out that only eNode B2 is the one which is failing, all other handovers were successful, then we can check if there was any PCI confusion. We can also add handover based offsets for eNode B2 only. So this can make our handovers more robust. If we, after trying all of that, we still see that we are failing for this neighbor relation, we can blacklist this neighbor relation and save our handover success rate KPI and also our drop rate KPI. So these are the things that we can do in this scenario where we have handover drops that are eNode B initiated. Now, other than that, we have MME drops. Now, what is a MME drop? MME drop means a drop where the MME sends a release to the eNode B, telling the eNode B that you have a drop. But as we will find out, most of the MME drops are not actually initiated by MME. They're actually radio drops, but because the eNode B does not know about it, so it thinks that it's an MME drop. So let's understand the scenario. So as we discussed previously, in Downlink, there is a number of RLC retransmissions that the eNode B can do. The similar concept applies in Uplink as well. So a UE also has an RLCD transmission count. If it exceeds that, it will consider it itself a drop or a radio link failure. So let's say the UE sent uplink data and the eNode B could not decode it. We have eNode B1 here, so it will keep sending the retransmissions until it has tried all of its RLC retransmissions that it is configured with. So if all of them fails, then the UE will think now that okay, I have an RLF, I have a radio link failure. Now, because the eNode B is not getting any of this, for instance, so eNode B might not know that the UE has already exceeded its RLCD transmissions. So eNode B might not know that this UE is experiencing a radio link failure. So in downlink, because eNode B was the one transmitting data, so eNode B could know that the UE was having a radio link failure. In uplink, the eNode B might not be aware of that. So in this case, what will happen? The UE then might try an RRC re-establishment. Now, if the RRC re-establishment request is on the eNode B1, then everything is fine. eNode B1 should make it successful, and we will say that the drop will not happen. But what if the UE is now trying an RRC re-establishment on another eNode B? Now, it can happen. It usually happens because a UE that is failing in uplink data over here, it might be in such a poor coverage that this UE will say that eNode B1 is no longer my primary source cell for source eNode B. So it might try it on another eNode B. So the other eNode B2, it gets the RRC re-establishment request. Now this eNode B2 will need to fetch the context of this UE from the eNode B1. Now if let's say the eNode B2 fails, or if there is no X2 link between these two eNode Bs, or they are not neighbors to each other, or let's say we do not have the feature active to request the context over X2, then the eNode B2 will not be able to get the context, and it will then send an RRC re-establishment reject to the UE. Now in this case, the UE will then need to send a new RRC connection request. So UE will initiate a new RRC connection request to the eNode B2. Now remember, as of now, the eNode B1 does not know that this UE has gone a radio link failure. It still thinks that UE is on the eNode B1. It does not know about that the UE that it is trying a new RRC setup on eNode B2. So the UE will go through the RRC setup. We have this whole process of RRC, message 1, message 3, message 4, message 5, and once the eNode B2 has received the RRC connection setup complete, so based on this one, the eNode B2 will then send an S1 initial UE message to set up the ERAB for this UE on eNode B2. Now the MME will check this message. It will look at the TIMSI inside this message, and it will say, okay, but I already have this UE connected to me from eNode B1. So if there is a new connection, that means I need to release this context from eNode B1 first. Only then I can add a new context for the same UE from eNode B2. So what it will do, the MME will then send a UE context release command to the eNode B1, indicating the eNode B1 that you need to release this UE, and the eNode B1 will think that because the MME sent me this command, and eNode B1 is not even aware that the UE had gone in radio link failure in uplink, so eNode B1 will think that this was an MME initiated drop and nothing to do with radio. While actually this is a radio drop. It was an uplink radio drop, which eNode B1 was just not aware of it. So it will peg it as an MME abnormal release, while it was actually a radio drop. And once the MME has done that, MME will send initial UE context setup request, which will start the ERAB setup for this UE on eNode B2. So in this way, the eNode B1 will peg a drop, which will be MME initiated drop, but as we can see, the issue was something on the radio, mostly in the uplink. So how do we solve this? Now again, one of the simplest case would be that we can just increase the uplink RLC retransmission threshold. If we do that, then if we, let's say, change it from 8 to 16, then the probability of this failure will be reduced and we will have lesser number of such drops. Another option would be that to improve our uplink uplink channel quality. That can be done by either optimization, it can be done by putting enhanced receiver algorithm like interference rejection, combining uplink FSS, uplink coordinated multipoint. So using all of that, we can actually improve our uplink link budget, we can improve our uplink channel quality, and we can reduce such kind of drops. So if we do that, these kind of drops will be reduced. So let's look at another thing now. Another one would be poor quality drops. Now if you remember, we have N310 and T310. Now what is N310? The UE in downlink is always looking for PDCCH. Now if the UE is unable to decode PDCCH for a certain amount of time, it will say that it is having an N310 failure. Now in LTE that is around 200 milliseconds. So that means 200 TTIs. So if the UE is unable to decode PDCCH for consecutive 200 TTIs, then it will say that it has experienced one N310 failure. After this, it is a 10 millisecond sliding window. So if I put N310 as let's say 2, then it will mean that 200 milliseconds and this is equal to 1 N310. And then if for 10 milliseconds more I am still unable to decode PDCCH, so that will make it N310 is equal to 2. So N310 is equal to 2 will mean 210 milliseconds. N310 is equal to 3 will mean 220 milliseconds, and so on. So N310 is indicated initially as a 200 millisecond PDCCH decoding failure, and after that it is a 10 millisecond sliding window. Now if the UE is unable to decode N310 for consecutive number of configured values, so if I have it configured at N310 is equal to 2, so a UE that failed to decode PDCCH for 210 milliseconds will then start T310, and within T310, if there is no N311 scenario and T310 expires, the UE will then trigger RRC re-establishment request. Now when the T310 is running, and within that if we have an N311, that means N311 is an in sync message, which means that the UE was now able to decode PDCCH for 100 milliseconds. So if we have that event, then the UE will stop T310 and it will consider itself that it's back to connection. So let's take an example. Let's say if my N310 is a value of 5 and my T310 is a value of 200 milliseconds. So what will happen is the N310 we know that 200 milliseconds, then 210 will be 2, 220 will be 3, 230 will be 4, and 240 will be 5. So N310 is equal to 5 means that if a UE is unable to decode PDCCH for 240 milliseconds, it will trigger the T310. And T310 is 200 milliseconds, so the total will be around 440 milliseconds, 200 plus 240. So if the UE is unable to decode PDCCH for 440 milliseconds, it will then trigger RRC re-establishment request. Now after this, the scenario is similar. If it has triggered an RRC re-establishment request to another eNode B which cannot fetch the context over X2, then it will reject the RRC re-establishment. The UE will then try RRC connection setup on that eNode B, and then that eNode B will send S1 initial UE message, for where the MME will think that okay, I already have this context, this UE's context from eNode B1, so I need to release that before I can accept a new context from eNode B2. So when the MME releases that, the eNode B1 will peg a drop which will be an MME initiated drop from the eNode B side, but in actual practice the UE failed over the radio link, and so the drop was more of a radio drop, but the eNode B is just not aware of it. So in these scenarios, what we can do, naturally we can increase N310 or T310, so that will increase the duration. And if we increase the duration for this drop to peg, then the probability of this drop being pegged will be lower. So let's say if I make N310 plus T310 is equal to 2000 milliseconds, then the UE will have to wait for 2000 milliseconds of consecutive PDCCH decodings failures, only then it will trigger that. So in that case, it will wait a much longer time, so the probability of this drop will be reduced. Another option can be that we can reduce N311. So if N311 let's say is equal to 5, that means that the UE will have to wait for 500 milliseconds of consecutive PDCCH decoding. So if we make it 1, then UE only waits for 100 milliseconds. So in this case, if N311 is a lower value, then also the UE can go back to in sync mode and much quickly. Another thing would be to simply improve the SINR by optimization. If we improve the SINR, then the PDCCH decoding will be successful and we will not face this problem that much. So that is another option that we can take. Okay, another one, handover drops, MME initiated. Now this is a similar scenario that we discussed previously, but the difference here is like this. Now if the UE gets the handover command and the handover is not being successful to eNode B2, then the UE tries an RRC re-establishment, let's say on another eNode B3, which is, let's say, not a neighbor, which cannot fetch the context, so it will reject RRC re-establishment. Then the UE will try RRC connection setup on the eNode B3, and the eNode B3 will then trigger S1 initial UE message to MME for this UE. And MME again will see that, okay, I will already have a context for this UE on eNode B1, so it will send a UE context release command to eNode B1, and eNode B1 will peg a MME drop. Now in this scenario, the difference between the previous scenario where the handover drop was eNode B initiated was in a scenario where the eNode B1's X2 relocation overall timer expired before this happened. So if the X2 relocation overall timer expires before the UE can start a new connection on another eNode B, then this scenario will be pegged as the eNode B initiated drop. If the eNode B's X2 relocation timer has not expired, let's say it's a big value, it has not expired, and the UE has already set up a connection to another eNode B, and that eNode B then when tries to set up the ERAB for this UE over the MME will send the UE context release command to the eNode B1, and in this case the drop will be pegged from the MME side. So it's simply a scenario where the eNode B1's timer of X2 relocation overall timer, how big is that? If it is too big, then most of these drops will be pegged under eNode B initiated. If it is too small, then most of these drops will be pegged under MME initiated. This drop will also peg in case of IRAT handovers. So if instead of eNode B2 this was an IRAT, let's say a 3G node, node, and if the UE was sent from eNode B1 to a 3G node and it failed, and then it tried to connect to eNode B3, which is a LTE node, even then this scenario will be pegged in a similar concept and a similar signaling flow. So this is how handover drops can be pegged as an MME initiated handover drops. So what we can do for them, it's simple. Similarly, the same thing that we discussed in the handover drops for eNode B initiated, we can do all of those things. Other than that, the RRC re-establishment for multi-target RRC re-establishment can also be tried, where the eNode Bs which are not able to fetch the context from the source eNode B can then fetch the context, and in that case the RRC establishment will be successful and we will not have a drop. So if we can enable RRC re-establishment context fetch over X2, that can also help in solving lots of our drops. Okay, another option can be a single UE repeated drops. It can be a single bad UE, a bad UE that can cause multiple drops. So this scenario can happen. So let's see what happens in this scenario. So a UE, let's say it's connected to this eNode B. After some time it triggers an RLF. So if a UE initiated RLF, then the eNode B will not be aware of that, as we discussed previously. Now this UE can try an RRC connection request on the same eNode B. Now this eNode B will not be aware that this is the same eNode B which already is connected to the eNode B. It will have the same TIMSI, but the eNode B might not be able to see that because eNode Bs usually do not read the TIMSI value. So in this case, the eNode B will send RRC connection setup, which eNode B will think it's a new UE, so it will give it a new CRNTI, a CRNT. So for eNode B, this UE is a different UE, but not the same UE that is already in the eNode B's context. So this UE will then send RRC connection setup complete, and the E node B will then send S1 initial UE message for this UE to the MME. Now MME will read this. MME will say, oh, that is strange, I have the same TIMZ for the same UE, the same context already exists on this E node B. So MME will think that, okay, maybe the old context might be stale, it's no longer valid. So MME will send an UE context release command for the old context, this one. So this release command will be for the old context. So E node B will then release this UE, thinking that this is an MME initiated drop, and after this MME will send initial context setup request for the new context, and in that case the E node B will then start a new setup for this scenario. Now in this scenario, what will happen is that the E node B will peg a MME drop, and a bad UE or a UE which has some compatibility issues, it can keep on triggering such scenario again and again. And if that keeps on happening, then the E node B will keep on having such ERAB drops. So to solve that, there are some vendors who have now added a new feature, a new algorithm on the E node B, where the E node B can check the UE context release command or the S1 messaging for TIMZ. And if it sees that, for instance, in this case, it knows that the TIMZ of this UE, and it sees a context release command for the same TIMZ, so it will not peg it at a drop. So if that happens, then what can happen is that we can reduce or exclude these drops from our KPI. So in this scenario, what we can do is that we can enable those algorithms, but in order to find this by ourselves, we would need to put L3 traces. So from level 3 traces, we can look into the RRC connection request or the S1 initial UE message and see if the drops are coming from the same TIMZ. If they are coming from the same TIMZ, then such features can be optimized, and these features can, these algorithms can help in excluding these kind of failures. So, but again, these kind of failures are mostly UE type issues. So that is something that we can only find out if we use L3 traces, and we can then look at the TIMZ level from the RRC connection request and find out that the UE is a single UE that is causing the problem. So this is some of the cases that we could cover from drop rate, and I also shared all the optimization actions that we can take. So hopefully it was helpful. If it was helpful, do subscribe, do like the channel, do share with your colleagues, and we will we'll keep sharing more information, we'll keep sharing more optimization actions. So thank you so much. See you. Bye bye.